In this video, we're going to talk about what Fourier cosine series and Fourier sine series are. So I want to begin with some background and talk about periodic functions, and then we'll use that to motivate what these things are, cosine and sine Fourier series. So we say that a function f is L periodic if and only if f of x plus L equals f of x for all x. Okay, so sort of the most common examples that we have of periodic functions are trig functions. So for example, sine is a periodic function. So I've drawn in the graph of sine of x here, and this function is 2 pi periodic. Because notice on the graph that where we are, for example, at 0 is, corresponds directly to where we are at 2 pi. So basically, my function sort of completes one period from 0 to 2 pi. And then if I were to keep drawing the graph beyond this, the function would look exactly the same, and it would keep repeating that shape again and again and again. Okay, so sine of x is 2 pi periodic. So notice that, like, if I really want to get technical about this, so this point right here is negative 2 pi. It is also true that this function is 4 pi periodic. So I could also, if I wanted to, it's also 4 pi periodic. Because it does repeat every 4 pi. In fact, any positive integer multiple of 2 pi would work. Like this also repeats every 6 pi. And it also repeats every 8 pi. So if I wanted to say this was 6 pi periodic, that wouldn't be wrong. I could also say that. Okay. So next I want to talk about the functions that show up in our Fourier series and what type of periodic they are. So I'm going to call sine of m pi x over L, I'm going to call that the function g of x. And I'm going to let h of x be the function cosine of m pi x over L. So both of these functions are 2L periodic. They'll sort of repeat every 2L. Okay, so in this formula right here, m is any positive integer in this sine function. So like 1, 2, 3, dot, dot, dot. All right, so what I want to do is I want to draw some examples. Okay, so first, I want to draw, in purple, a function that represents my sine graph when m is 1. So when m is 1, we'd have sine of pi x over L. So sine of pi x over L. So this is when m equals 1. Okay, so if I were to draw this, this will look the same as the sine graph that I drew above. It's just it'll either get compressed or sort of stretched out, depending on what L is and how big it is. Okay, so I'm going to draw something that looks like my sine graph. So let's start it at the origin. So it'll rise up, and then it'll start to fall when I get to, and then I get to L. And then it'll keep falling and reach a low point here, and then rise up again until I get to 2L. All right, and then I could draw that tending in this negative x direction. So it's going to start to fall, start to fall, start to fall, reach a low point, and then start to rise until I get to negative L. Keep on rising, start to curve a little bit, and then fall when I get to negative 2L. Okay, sorry, that last part wasn't great. Let's fix that. I start to fall until I get to negative 2L. So next, let's draw a graph for what happens if m is 2. So this would be sine of 2 pi x over L. So this is when m equals 2. So when m equals 2, what that's going to do is that's going to make it oscillate up and down twice as often. So instead of reaching a high point here, it's going to reach it sort of, twice as fast. It's going to reach a high point here. So let's start to draw this graph. So I'm going to start it at the origin again, and it's going to go up until it reaches this high point, and then it's going to start to fall. And notice that it's reached the x-axis twice as fast as it did before. So this is L over 2 when it's reached the x-axis. Okay, and then it'll start to fall, reach a low point, and then tend back up. So notice that it's sort of completed its period twice as fast as it did before. Before, the sine graph completed its period at 2L, but now it's completing it at L. Okay, so now let's draw it in the negative direction as well. So in the negative direction, it would fall, reach a low point, and then start to rise, and then keep on rising, and then start to fall, and then it'll come back down at negative L. All right, so that is the graph of my sine function when m is 2. Let's also draw a graph of one cosine function. All right, so the cosine function, I'm going to draw a cosine function when m is 1 again. So this would be cosine of pi x over L. So this is when m equals 1. So a cosine function like this, if you plug 0 in for the x, you get cosine of 0, which is 1. So its y-intercept is going to be at 1. It's going to start up here. And then it's going to begin by falling, go through that same, actually, x-intercept as the light blue graph. And then it'll continue to fall, low point there, and then rise, crossing the x-axis, and then rise and reach a high point there. And I could draw it in the negative direction as well. So in the negative direction, it'll fall, cross there, and then it'll sort of reach a low point here, start to rise, keep on rising, but slow that down. Okay, and that's the graph of my cosine function. But notice that cosine also has so all of these functions are 2L periodic. They all repeat every 2L. In fact, the sine of 2 pi x over L graph, this light blue one, we could actually say that's L periodic if we wanted to, because it actually completed its period twice as fast. But it's not wrong to say it's 2L periodic, because it also repeats every 2L. Okay, so the m in these formulas, it represents how many times these functions oscillate on the interval from negative L to positive L. So by oscillate, I mean, like, how many times do they sort of complete one full cycle, or one full period on this interval? All right, so now I want to start to tie this in with Fourier series a bit. Okay, so I want to state a key fact about Fourier series. So a key fact about Fourier series. Okay, so the key fact is, okay, I don't want to go too far. So when we talk about a Fourier series for a function f of x on a closed interval from negative L to positive L, if my function f of x was an odd function, then its Fourier series would only have the odd terms. And what I mean by that is the sine terms. It would only have sine terms. So sort of conceptually, the reason why that's happening is because all the sine terms are odd functions. And when you sum a bunch of odd functions, you'll get an odd function. Okay. When f of x is an even function, then the Fourier series for it will only have cosine terms. It'll only have the even terms. And if f of x is neither, if it's not odd and it's not even, and that could happen, then f of x will have, the Fourier series will have, that's what I mean. So the Fourier series will have both cosine and sine terms. All right, so I would really encourage you at this point to pause the video for about 30 seconds, maybe a minute, and think about why. So I'm not going to count it down like I normally do in the videos. I'd really encourage you to think about this though. So it has to do something with what the coefficients of the Fourier series end up being. Like for my Fourier series to only have sine terms, that means all the coefficients of the cosine terms and the constant term, they all have to be 0. So that's what I kind of want you to think about. Why is that happening? Okay, but we've seen examples of this happen. For example, back in section 10.3, when we first talked about Fourier series, we found the Fourier series for absolute value of x on the interval from -1 to +1, and that didn't have any sine terms. And that makes sense according to this observation, because absolute value of x is an even function. So its Fourier series is only going to have cosine terms. All right. So the key thing that we're going to be interested in doing in this section is we want to be able to write functions in terms of a Fourier series that only has cosine terms or only has sine terms. All right, so I've stated that goal. We want to be able to write a function in terms of just cosine terms or just sine terms. So I want to talk about the key idea behind this. So it'll turn out that this is going to be doable when our function f has domain 0 to L. So in general, when my function has a domain from 0 to L, we are going to be able to do this. And the idea behind it is, if the domain of my function is just from 0 to L, what we will do is we will extend the function. So we'll sort of add to it, we'll sort of add to the graph, extend f of x, so it becomes even if we want cosine terms, or it becomes odd if we want just sine terms. Okay, so now this is going to take us to the idea of extensions. So let's let f of x be piecewise continuous on the interval from 0 to L. So I'm going to define two functions. And these two functions, so one of them is called f sub e of x, so f e of x, and the other one is f o of x. Okay. So the idea behind this is I want this function f e of x, I want this to be even. And I'm going to want the function f o of x to be odd. So I've drawn just kind of like a sample graph of what my function might look like. So notice that it's defined on 0 to L. And it doesn't have to be continuous the whole way. It's fine if my function is piecewise continuous on that interval. All right, so I'm going to define this function f e of x now. So I want f e of x to contain what f of x is. So one of the pieces is going to be f of x. So it's going to be f of x on the interval 0 is less than x is less than L. Okay, and now I also need to define it from negative L to 0. So if negative L is less than x is less than 0, the way we're going to define this function to make it even is we'll say that it is f of negative x. And if we do that, that'll sort of guarantee that the negative x values, that the function will be the same as what it is at the corresponding positive x value. So I think it'll be easier to see what that means when I draw a picture of this. So I'll do that in just a minute or two. So first next let's define this function f0. Sorry, fo, not f0. So this one I want to be odd. So I'm going to start it off with a piece that's just f of x. It's f of x if 0 is less than x is less than L. And then I need to now define it if negative L is less than x is less than 0 in such a way that it's going to make it odd. And if I want to make it odd, I should let this be negative f of negative x. All right, so this function f e of x, so f e of x is sometimes called the even 2L periodic extension of f. And then fo of x is referred to as the odd 2L periodic extension of f. So the word extension means I'm taking what f is, what f of x is, and we're just sort of extending the graph. We're adding more to what the graph will look like. Okay, so with both of these functions right now they're just defined on the interval from negative L to positive L. But we could extend these, we could extend both to all real numbers, negative infinity to positive infinity, so they are 2L periodic. So that's what we're going to do next with these formulas. We're going to not just define it from negative L to positive L, but we're going to extend them on negative infinity to positive infinity by just repeating what happens and making this 2L periodic. All right, so let's draw a graph. Okay, so let's start with Fe of x, and then I'll draw a graph of Fo of x. All right, so let's draw some axes. Okay, so what Fe of x will be is, start off with the graph of f of x. And in my definition here, actually I have it already. So in my definition of Fe of x, notice that I haven't written equal sign when I say 0 is less than x. As a result, I'm going to put an open circle here. And then I draw my graph of f of x. And then there's no equal sign when x equals L either. So I put an open circle there as well. So I'll comment more about that, why there's no equal signs there, after I draw the graphs of these. Okay, so now what I want to do is, I need to draw this other part of Fe of x. Well, what this other part will do is, it'll sort of make this function even. So in between where negative L is, and 0 is, I need to draw something that'll make this even. So that'll look like this. So notice at like a negative x value and its corresponding positive x value, their outputs are the same. So okay, so that's making this even. And the next part of this is, well, we can extend this to negative infinity to positive infinity in such a way that makes this 2L periodic. So we're just going to keep this going. If I keep this going, I keep repeating this pattern now. So it sort of goes down and then up, makes that sort of V shape. And then here as well, it goes down and then goes up, makes this V shape, and then you're able to keep on going like this. I could keep on going like this forever, and now it's 2L periodic. All right, so now let's draw Fo of x. So what does this odd extension look like? All right, so let's draw our axes. Okay, so I begin in the same way by drawing f of x. Okay, so open circle there, because we don't have equal signs in this chain of inequalities. But now I have to extend it on the other side of the y-axis to make it odd. Okay, so to do that, it's got to be symmetric about the origin. So I'd end up taking this open circle and sort of putting its mirror image down here, and then drawing something like this. That is now going to be symmetric about the origin. So if I think about some x value here, and its negative x value here, their corresponding y values are opposites. And that's what this function definition says should happen. Okay, but now we can extend this more so that it's 2L periodic. Okay, so if we make this 2L periodic, so also here is where negative L is, what we do is we'd continue this shape. So after we reach this open circle, we drop it back down, and then go up. And then now do this upper piece. Okay, so we're sort of repeating the shape again and again. So on the other side, we draw that top piece, go down, and then this bottom piece, and then it keeps going like that forever. So that's the odd periodic extension. So the reason why there aren't any equal signs in these inequalities for the odd function are, if we did put an equal sign like here and here, for example, what that would do in terms of the graph is it would fill in this circle and it would fill in that circle, but now it's not a function anymore. It's not a function anymore because I can't have two, it doesn't pass the vertical line test. This at x equals 0, now I have two different y values. I have two different points, and that wouldn't be a function anymore. All right, so let me go ahead and erase those. Okay, so I've gone ahead and erased those circles as well as those equal signs on these inequalities. So that's why I don't include equal signs there, because it might affect whether this thing is a function, whether this extension is a function. And then I just adopt that same convention for Fe of x, for the even extension. Although for the even extension, we actually don't run into that issue of it not being a function anymore. So if we wanted to put equal signs at some of these, we could for the even one. So next, let's talk about what the Fourier series for these two things look like. All right, so the Fourier series for fe of x will just have, because it's an even function, we'll just have cosine terms. And moreover, it's going to approximate f of x. So remember, f of x was just on this part of the graph. It'll approximate f of x on the interval from 0 to L. The Fourier series for fo of x, the odd extension, will just have sine terms, because this is an odd function, and it's going to approximate f of x, the original function. So here was the original function on the interval from 0 to L. All right, so now let's write down what the coefficients from our Fourier series would look like. So let's do it for fe of x, for this even extension. So those coefficients look like a sub n. All right, so in the case where n is greater than 0, for example, what would this look like? So remembering what this was from last time, so using our inner product notation, we have the inner product of, so we're doing the Fourier series for fe of x. So we have fe of x with cosine of n pi x over L, and then divided by the inner product of cosine of n pi x over L with itself. So cosine of n pi x over L. All right, so now if we evaluate what these are, so the top is going to be the integral from negative L to positive L of fe of x times cosine of n pi x over L dx. And the denominator is going to be the integral from negative L to positive L of cosine squared n pi x over L dx. Okay, so now let's think about whether these pieces are sort of even or odd. So cosine squared is definitely even. Fe of x, the way we constructed it, this was even. And cosine, this cosine term is also even. And an even times an even is even times an even is even. So let's use our symmetry to now express these integrals in another way. So because this function on the top is even, we can write it as 2 times the integral from 0 to L of the functions multiplied. But on the interval from 0 to L, fe of x is the same thing as f of x. Okay, so that's important. And then it's still multiplying by cosine of n pi x over L dx. And then we could do the same thing on the bottom. We'd get 2 times the integral from 0 to L of cosine squared n pi x over L dx. All right. So now notice that these 2's cancel. And what we have is we have an integral on the top and an integral on the bottom. And both of these integrals go from 0 to L. So what I'm going to do is I'm actually going to define a new inner product, just a slightly different one, where my integral is going to go from 0 to L instead of negative L to positive L, like it was before. So I'm going to go from 0 to L, f of x times g of x dx. So this is going to be my new inner product. And when we do that, the fraction that we have is going to become the inner product of f of x with cosine of n pi x over L on the top, and then divided by the inner product of cosine of n pi x over L with itself, cosine of n pi x over L. So this is what our coefficients of our Fourier, this is the Fourier cosine series, will technically look like. So we're ready to define it now. Okay, so our definition of the Fourier cosine series for a function f of x on the interval from 0 to L is, so now we're trying to approximate f of x purely in terms of the cosine terms, and then we also have the constant term in front, because the constant term is even. So the formulas for these coefficients are the same as what we saw before, just we have a new inner product. So a naught over 2, for example, is the inner product of f of x with the constant term 1 divided by the inner product of 1 with 1. So what I mean there when I say the constant term is this 1 was the term in the orthogonal basis that we talked about in section 10.3. Okay, and then an has this formula that we've seen before, the same fraction. But now you're sort of projecting onto the cosine terms. Okay, and the new inner product is going from 0 to L. Okay, so that's sort of the key difference for the coefficients with the Fourier cosine series. In the inner product, the integral goes from 0 to L instead of negative L to positive L. So similarly, now let's define this Fourier sine series. So here is the definition for the Fourier sine series. Now we're writing f of x purely in terms of the sine terms, and we have the same type of formula for bn for the coefficients. This fraction looks the same as what we saw before in section 10.3 on Fourier series. It's just the inner product now is slightly different. We are integrating from 0 to L instead of negative L to positive L. So one quick way to remember what this inner product will be from, whether it's negative L to positive L or 0 to positive L, is if a question is asking for the Fourier sine series or for the Fourier cosine series, the function is going to be defined on 0 to L. So I just stay consistent with those numbers in this integral. If it's talking about a Fourier series, just generally, the function would be defined on negative L to positive L. So my integral would also go from negative L to positive L. So that's one quick way to sort of just verify. Okay, so the last thing I want to mention in this video is in the textbook, they give slightly different formulas. I shouldn't even say slightly different. They give formulas that look different for a sub n and b sub n. Because what they do is they sort of basically evaluate what these two inner products are and express them in the following way. So in the examples I do, I'm going to be using this inner product form more because I like this conceptual interpretation of it, and I think it's easier to remember because it connects to our concepts of orthogonality. So in the next video, we will do an example.